All right, so let's get started and welcome everyone. Pardon me for not being able to turn on video. I cannot do it today. But today is the last TEPS seminar for the year. So watch out for emails for the request for recommendations for the next group of speakers. But for today, we have two trainees who's going to tell us about their awesome research that they're doing. So we have Jahnavi Shah, who's going to go first, and Pruthviraj Acharya, who's going to go next. So I will let their colleagues and advisors introduce them.
Okay, I guess I'm not Jahnavi's advisor, but I am her peer. I also work with Dr. Catherine Neish, but she could not be here today, so I'm here to just introduce Jahnavi, who is a third-year PhD student working with Catherine on Titan, and today she's going to show you her work on modeling impacts on Titan, as well as using some Earth analogues, I think, as a way to compare the two.
Thank you, Josh, for the introduction. I'm just going to start sharing my screen. Can I just get a thumbs up to make sure that it's working? Okay, thank you. Thanks, Josh, for the introduction. As you mentioned, I am Jahnavi. I'm a graduate student at the University of Western Ontario, advised by Dr. Catherine Neish. I want to say thank you to everyone for being here on a warm Wednesday. Today, I'm going to talk a little bit about my thesis. So the overall theme is the impact cratering process on Titan, but it's sort of broken up into two projects. So I'm going to give you a rundown of the two different things that I've been working on for the past couple years. So I wanted to start off with a little bit of background of why we care about impact craters. So impact craters in lay terms is basically a circular depression that's formed by asteroids or comets hitting the surface of a planetary body. And we actually see this on most solid surfaces throughout our solar system. And they're really interesting and important because they provide sort of the geological history of a surface, which is why we're interested in studying them. So on the left here, we have an image of meteor crater, or also known as the Behringer crater, which is a prime example of an impact crater on Earth. And on the right, we have a picture of an impact crater on Titan, and it's called Momoy crater. So why Titan? So Titan is the largest moon of Saturn, and it's actually the only other planetary body in our solar system that has liquid on its surface in the form of liquid methane. And that makes it very similar to what we see here on Earth. And in addition to liquid on its surface, it also has a very thick atmosphere, which is also comprised of nitrogen and a little bit of methane. So what's interesting is that the thick atmosphere has a complex climate system, and it has surface features very similar to what we see on Earth, which makes Earth a very good analog to study this planetary body. In addition to the liquid and the atmosphere, there's also organics present on its surface, which makes it very chemically rich, and we're interested for the astrobiological significance of the planetary body, which is why we want to study Titan. So the first project that I'm going to talk about is a comparative study of impact craters on Earth and Titan using radar images. So as I mentioned, Earth and Titan both have this very thick atmospheres. So it makes it very difficult to study with optical images. So a good technique to study these planetary bodies that have these thick atmospheres is using radar. And what that basically is, how it works is that a radio wave is transmitted and it hits the surface, and its backscattered echo is what creates images. And the echo, the backscatter of this signal, depends on the surface slope, the composition, and the roughness, which are all important properties when you're looking at craters, when you're trying to identify craters, and when you're trying to study them. So the motivation of this project comes from the fact that both these planetary bodies have a very low crater count. So on the left, we have a radar mosaic of Titan as mapped by Cassini radar. And the red dots represent all the craters that have been mapped to date. And that's a total count of about 90. Now, this is very low compared to its neighboring satellites. For example, Rhea, another moon of Saturn, has thousands of craters. And on the right, we have a global map of the confirmed craters on Earth. It's the yellow ones. It's a bit harder to see because they're a little bit scattered, but the total count is 201. Now, this is much larger than Titan, but if you think about, if you've ever seen our moon through the telescope, you can see that it's covered in thousands of craters. But because they're neighbors, it's a little, we would expect to see the same on Earth. And we think that there's low crater counts on both these surfaces because of its thick atmosphere. So, the asteroids or comets, they burn up before they hit the surface. And another big reason is that erosion, so there's active processes on the surface. So erosion and burial of craters, which might be erasing the craters and make them undetectable in orbit. So as I mentioned, because Titan is so similar to Earth, and we have a more solidified database on Earth, because we're able to map these craters, not just with remote sensing techniques, but with field studies and more than one data set, remote sensing methods. So we want to compare it to the Earth crater population to better understand the craters that we're not seeing on Titan. And as I've mentioned, radar is the best way to do this. So to have a study that translates, we want to study these impact craters here on Earth using radar remote sensing. So how the setup is, here I have an example of craters on Earth and Titan. So the top panel are examples of fresh craters. And by fresh, I mean something that's a little bit more preserved and the signature is more visible in radar images. And the bottom is of more degraded craters. So on the left, we have an image of, again, meteor crater, the one that we saw very originally. As you can see, there is a bright rim, which is indicative of so there's a bright radar feature, which means there's an uplifted rim, and the middle is a little bit darker, most likely due to, infill of sediments, which is also what we see on Titan. And on the right, we have an example of a similarly fresh crater on Titan called Synlab crater. And then when we move to the bottom one, we can see on the left, the Guanifata crater in Chad. The bottom half of its rim is sort of being infilled and eroded away, which makes it harder to have a proper boundary on this crater. And very similarly on the right, Soy crater on Titan, the boundaries are not as distinct. So this is essentially what I'm doing. I'm looking at all of the craters on Earth that are exposed to the surface. So out of the 201 that we have, about 60 of them are actually buried. So there's no surface expression, but the rest of them, theoretically, we should be able to see through radar. But we want to calculate how many we see and how many we don't see. And for this, we're using two different types of radar sensors. The specifications are not important, but basically the radar wavelength is sensitive to the roughness at the same scale. So we wanted to investigate using two different wavelengths. So I wanted this to be a little bit more interactive so people can participate. So we're going to look at some examples of radar images of craters here on Earth. And I want you to take a couple minutes, a few seconds to try to find the craters in these images. So remember, what we're trying to look for is a circular feature that has sort of a bright rim and a darker interior. If you think you see craters, you can tell me the number of craters you see in the chat, or if you're feeling inclined, you can raise your hand and tell me where you see it. But these are fairly easy examples. So I will point them out. They're right here. And I hope that's what people had picked out. Let me know if you saw something different, if you saw a different crater somewhere. But yeah, so on the left, we have an image of Caracol crater. And on the right, we have a picture of Lonar crater. So these are fairly easy examples, but it gets a little bit more challenging. So here we have an image of a radar image of a crater. And this is your challenge to find the crater or craters in this image. It definitely took me a while to find this crater, and it's not as easy. And so to give you a little bit more context, this crater is located in Brazil, where there is a bit of uneven vegetation cover, which makes it a little bit challenging to detect craters. I see something in the chat. I'm not sure I can access it. Oh, one in the bottom left. That is a good guess. That is a good guess. So what might help is Ooh, center right, just north of the mountains. That's also a really good guess. So one way I've been trying to sort of enhance the visibility in radar images is by adding topography data. So if I advance the slide, maybe now you can take a closer look again and try to see if your original guess was correct, or if you see any other craters now that we've added some elevation. So I think someone mentioned that just to the right. So remember, it's this circular depression. So the topography data helps us identify that. And here's another example. I'd be interested to see how many craters you think there are in this image. And so now I'll add the elevation data. Isaac says, when's a volcano? No, don't give away the answer. But yeah, you're correct. So it's a little bit more, so for someone who hasn't really looked at, geological features or, radar data before, it wasn't as clear to me, but you're right. It doesn't have that distinct bright rim, so it might be a little bit easier to pick out. But when you have really large images and you don't exactly know where the crater is located, it becomes a little bit difficult. So for another reason for topography data is that it helps us identify something that's an elevated feature. So like Isaac said, it's a volcano to the top left, and the bottom right is where the actual crater is. Right there. And so here are just sort of general examples of what I've been trying to do. Oh no, so sorry. Just give me 1 second. Okay. So I've been trying to categorize the visibility of all the exposed craters. So on the left is an example of the one that's most visible. It has that bright rim that we talked about. The middle one is a lake, which makes it a little bit ambiguous to pick out. And on the right is the most degraded one where we don't see it at all. So here is what that looks like. And so what we find is that out of all the craters that are theoretically supposed to be visible in radar images, only 50% are visible. And this visibility increases by 10% with the addition of topography data, which actually we don't have a lot of for Titan. So in the future, if we had more topography data, we could potentially identify 10% more craters. And so the goal of this is to, if we can apply this to Titan, we can better constrain the population. So if, for example, a very first order translation is maybe 50% of these craters are not visible in the Titan radar imagery as well. So surface age of Titan could be twice as old. So we use a lot of crater counting to determine how old the surface is. So if we're missing half the craters, maybe Titan is twice as old. And so just the previous few slides where I was getting people to look at the craters and help identify them also helps us understand sort of the observer bias when we're looking at these images. So there's an undergrad who's working with Dr. Neish over the summer to sort of launch a crowdsourcing project. And maybe this group would be a good one to advertise that too. So if you're feeling, like you want to find some craters and radar images, maybe we'll share the link to this group as well. But yeah, so that's sort of the takeaway from this first study. I'm going to just quickly mention the second study that I'm working on, and it's focused on sort of understanding the crater depths of fresh impact craters on Earth, on Titan. So as I mentioned from the previous project, erosion plays a big role in erasing these craters. So we want to better understand how much erosion actually takes place on Titan. And one way we do that is we compare it to similar sized satellites that don't have that atmosphere or those active processes which would help erase it. So Ganymede, which is a moon of Jupiter, is a great comparison because it has a similar composition, a similar size, which means that craters of similar sizes should behave the same way and should have the same depths. But what previous studies have found is that Titan craters of similar size, craters on Ganymede, are much shallower. So we know that there's some sort of degradation by fluvial erosion and aeolian infill on Titan. But previous models have used the assumption that they both have a similar thermal gradient, but that's not a fair assumption because there's presence of methane on Titan, and it's a slightly different composition. So what I want to look at is a modeling approach which can incorporate the differences between Titan and Ganymede so that we have a better estimate of what the depths of these Titan craters actually are. So from the initial runs, we find that Titan craters would start out even more deeper than they would on Ganymede, which means that the erosion is a lot more than we have thought previously. And the way I'm doing this is by using a shock physics code, which basically simulates the formation of these impact craters with specified parameters. And what I'm most interested in looking at are how the different crustal properties affect the crater morphologies. So mainly the thickness of the ice crust, the size of the impactor, and the temperature gradient of the ice. So on the right, I have a quick video of a very preliminary run. So here on the x-axis, we have the horizontal space. The y-axis is the depth, and the color bar represents the density. So what we have here is a 50-kilometer thick ice crust over a liquid water ocean, and we have an impactor of 10 kilometers hitting the surface. So you can sort of see what this model does. It models the formation of it. So as the shockwave travels, it deforms its surface. And in the end of the model run, we'd be able to extract the depth of the final crater, which is what we're most interested in. So the goal of this project, because it's still in its early phases, we want to run the simulations for varying parameters. So the parameters that I mentioned earlier, the different crustal properties, we want to test different values for that are most suitable for Titan and Ganymede. And then we have Cassini observations of these craters on Titan, and we want to be able to compare the model outputs to the observations. And as I mentioned, this will help us better understand, better constrain the amount of erosion that's present at Titan craters because we know it's a process that degrades these craters. And it will also help us better understand how crustal properties influence crater morphologies. And it's important for NASA's Dragonfly mission, which I think there has been a TEPS seminar back earlier in the year. So the landing site, or one of the sites of study for Dragonfly is Gale Crater. So eventually we would want to do a case study for a south-sized crater to make predictions of what Dragonfly will find when it gets there. And yeah, so I'm happy to take any questions. Thank you for your time.
Great, thanks, Jahnavi. Questions?
Do we raise our hand or how do we ask questions?
You can raise hand or you can speak up as you have done so.
Okay. Very nice presentation. Thank you. I like that you're doing those two aspects. Can you talk a little bit how the wavelength of the radar affects your detections?
Sorry, I think I cut out for a second.
Oh,
can you repeat that, Isaac? Sorry.
Of course. Can you talk a little bit how the wavelength of the radar changes your ability to detect the craters?
Sure. So actually, the initial reason why we started off with the two different wavelengths was we thought there might be a difference because, in studies where we've looked at, studies that have looked at X-band, which is much smaller, they've been able to find underlying features of craters, like you will find fluvial networks, which helps us identify that more. But with the C-band and the L-band, at least from my analysis, I haven't found a difference between the two wavelengths and how that affects the visibility. It seems to be fairly consistent. If it's visible in one, it's visible in the other, minus just a few examples where it's visible in one and not the other. But I haven't found a trend with the wavelength itself.
Okay. Yeah, I was wondering because sometimes vegetation, or in the case of Titan, maybe sand-sized grains that are thicker than a meter would absorb all of your radar signal.
Right. Also, the other thing is that it's not exactly comparable to Cassini radar, which is one of the limitations. But you're right. Maybe if we had a longer wavelength.
Okay, thanks.
Any other question?
I have another one if it's all right.
Yes, please.
Go ahead.
So sometimes we use polarization to extract more detail out of it than showing a single image. Are the images you're showing, are they polarized, or are they showing everything? And then how would you use polarization?
Right. So I've tried to look at like vertical, horizontal oriented polarization, or just, just one like single polarization. The problem that I run into is not all of the images that are available come in both dual polarization. So I haven't been able to do a proper analysis if that would affect the visibility. And with using the C-band, the Sentinel data, it's just very computationally, it just takes a long time to process both the dual polarized data. So I've just been looking at the single one. But we found, at least in the initial sensitivity study, I don't think I've done like, VH or HH, it didn't really change much. And especially if I'm just looking for the general visibility, it hasn't shown a change. But maybe if we were looking for specific features of the crater, maybe that's where it would be most useful. But yeah, we just computation and lack of data.
Okay, yeah, thanks. Yeah, it makes sense that, you'd have things that are radially symmetric rather than linear. But yeah, if you're looking at individual features or cracks or something, you might be able to detect them better.
Right. Those are great questions. Thanks, Isaac.
All right, great. Let's thank Jahnavi again.
Thank you very much.
And let's move on to our next speaker. So we have Prithvi, and he will be introduced by his advisor, Isaac.
Hi. Yeah, so I feel comfortable speaking up today because I know I'd talk again. So it's my pleasure to introduce Prithvi. Prithvi is a student working in my lab. He joined my lab a couple years ago as an undergraduate, and he decided to stick around for his master's, and I'm really, really happy that he did, because the work he's doing is really quite fantastic. I originally gave him a project looking for clouds near the surface of Mars, and then I gave him 2 data sets to compare. And then from there, he went way beyond anything I imagined, which is just truly fantastic because he's got so many great ideas. And so he's really a role model for my lab in 2 ways. One is the great ideas, but also all the terrible ideas he comes up with, because he doesn't feel bad about it. He's like, I got 50 ideas, I'm going to try them all. And I think it's just a wonderful method for science, is to think about everything and try it all. So with that, I would like to introduce Prithvi, and I'm glad that he can present today.
Thank you, Isaac. Share my screen. You guys can see it, right? All right, perfect. Yeah, so my project was to monitor the northern sea seasonal cap of Mars using computer vision. The image that you see right now was taken by the Hubble Space Telescope during a global dust storm, which is when the entire planet just gets covered in like a massive dust storm. But the thing that really stands out to me personally are just the polar caps of like Mars. They can be thousands of kilometers in circumference and can actually make up a significant percentage of the planet. And they need to be considered when looking at the planet on the largest scale. So due to their massive size, they have huge influence over the entire planet. Some places on Mars have seen pressure changes by up to 30%, and also greatly changes the atmosphere composition because they act as massive source and sinks for the atmosphere. One place that kind of highlights this the best is at Gale Crater, or the pressure variation at Gale Crater. Which is about 5 degrees south of the equator. So it's basically right next to the equator. During southern wintertime, we see a huge decrease in the pressure as the southern cap is being formed. And then we see an increase in the pressure as the cap sublimates. And then during northern winter or southern summertime, the pressure decreases again as the northern cap is being formed, but not as large, just because the southern cap is so much larger than the northern cap. So the polar caps are also very dynamic. There's a huge amount of activity in and also around the polar caps. Here's a short little GIF taken by the Mars Express orbiter showing this massive dust storm coming off the edge of the seasonal cap, the northern seasonal cap, and then moving right up to near the equator, maybe even past the equator. I'm not really too sure, but it's just massive dust storm showing huge amount of material being transported. Also, you can kind of see how the storm kind of moves counterclockwise along with the polar vortex, kind of sweeps out a very large region. The image on the right, that's taken by the Mars Global Surveyor. This is kind of mid to late spring. This kind of shows another pretty large dust storm, not as large as the other one, but still significantly, but still like hundreds of kilometers wide. I like this image because it shows a bunch of water ice clouds around the seasonal cap and just in the region, in like a general kind of showing huge amount of water just being moved from the North Pole towards the south. So there's two main ways by which we can monitor the seasonal cap. First way is by taking spectral observation and getting the surface temperature and following the 150-degree line. This is the temperature when CO2 sublimates on Mars. This lets us track the seasonal CO2 cap. The second way is by taking large-scale visual observation. This one over here was taken by the Mars Color Imager. They both have their advantages and disadvantages. The spectral observation lets us see the formation and also the sublimation of the seasonal cap, but it's very hard to see these dust storms that kind of help us to understand what's happening right up at like the surface. The visual observation can see those dust storms, but it cannot see the formation of the cap. So I'm quickly going to go over some important terminology, which you'll see throughout the presentation. First one, it is solar longitude. This is the position of Mars along its orbit. So solar longitude is 0, that's the spring equinox for the northern hemisphere. 90, it is summer solstice for the northern hemisphere, and then the opposite season for the southern hemisphere. Another one is Mars year. This is the current year on Mars. So Mars year 1 was in 1955, and then currently I believe we're on Mars year 36. So the work that I've done closely follows the work done by Kelvin and all in 2015, where they used large-scale Marcy observations to manually outline the cap and find the recession rates for 7 different Mars years. Since they're doing this entire process by hand, this was a very time-consuming process, and they're like using about 20% of the total data that was available. So this kind of led into it. It was very hard to see many sub-seasonal trends. And they did try to automate this entire process to kind of use the entire data set. But the water ice clouds coming off the seasonal cap, they proved to be problematic when they were using RGB color detection. So when I was coming up with how to track this, I knew I couldn't use RGB color because that's been used before and it didn't quite work. And also around the same time, I was TAing for this color theory course, and they talked about how RGB color couples important properties of the color, such as the saturation and the brightness of the color. So that's why I went with HSV color format, which stands for hue, saturation, and value, or the brightness of the color. So decoupling these important properties has some beneficial effects for my particular project. Firstly, I can completely ignore the water ice clouds. So if I were to take this RGB image, this is a Marcy RGB image, and decompose it to its HSV value. So in the hue channel, we see it's very dark. This indicates that the image is being dominated by the red hue, which is what we expect to see for Mars. The value channel, which is kind of what we expect to see from a grayscale image. But in the saturation channel, we see that the water ice clouds are much less saturated from the seasonal cap. So in this channel, by setting the appropriate bounds, we can completely ignore those problematic clouds. Another reason why HSV detection is good, because it's very robust to external light changes. Since the brightness of the pixel or the color is decoupled from the other two channels, we can accommodate for light changes, which is really important because I'm going from early spring to late spring, during which the entire northern polar region gets brighter as the sun gets higher in the sky. So the entire automation, which you can see on the right, was written in Python, and the backbone of the code was made by using libraries such as OpenLikeCV, which is an open source computer vision library. Not going into too much detail in this, but essentially found the appropriate HSV bound, fit an ellipse over it, and then kind of went through a filtering function to refit the white ellipse, which you see over here. And I tracked the semi-major axis versus solar longitude and also the area of the ellipse. So if I could go and find the trends, I had to verify whether my method was actually even right. So comparing the outlines between my method, which is on the bottom over here, and the manual method, we see strong resemblance between the two outlines around the same time. Although the thing that really stands out is the manual method is very smooth. Is most likely due to human nature drawing, outlining the seasonal cap, whereas my method looks at the individual pixel value, so it's very coarse and rough. Comparing the data points directly, we see that Kelvin and Alps data points and the ellipse fit and the ellipse fit points, which are the blue ones, have very similar recession rates, but my points on average were a bit smaller than theirs. At most, they were, I believe, a degree smaller than what they used. But if I impose the same circle of best fit that they used, which is the green points right over here, the difference shrinks dramatically. It goes from maximum of 1 degree to about 0.3 degrees. So the outlines are the exact same, but the difference arises from using different shapes. I believe an ellipse fit is a better fit than a circle fit, just because mid to late spring, the seasonal cap has a very non-circular shape, and so an ellipse with its higher degree of freedom can better accommodate for this weird shape of the cap. So I'm going to quickly go over two of the interesting trends that I've found. First one is the sudden latitude increases that happen, where the recession rate just kind of jumps. The second one are the effects of the global dust storms, where the entire planet is covered in dust. So Mars year 29 and 30, which is 2008 and 2009, they experienced a sudden increase in their latitude by about 2 degrees and lasting about 4 or 5 days. And they have a very similar shape. You see this increase right over here. Hopefully it's clear enough. And then afterwards, the recession rate kind of plateaus off, and then it continues again at a linear rate. If I compare the recession rate before and after this increase, I saw that the recession rate after the increase was slightly higher than it was before. So that was pretty interesting. And secondly, comparing what's happening at the comparing what's happening at the images, I noticed that there was a very reasonably large regional storm happening at around the same location. This kind of indicates that maybe topographically driven, but I'm not too sure. So what I think is happening is before the increase, the cap is slowly receding due to the sun. So I like the rate which the sun gets higher in terms of latitude. Then there's a major sublimation event happening that shrinks the seasonal cap, resulting in these dust storms that we see throughout the cap. Then the recession rate kind of halts since the primary driver for recession is the sun, and the cap has shrunk. The sun actually needs to catch up before recession could actually continue. Then once the sun catches up, recession continues, but now it's being enhanced by surface winds that are occurring around the same time. And the surface winds are actually shown in previous work that they actually enhance sublimation. So now the sublimation rate is actually enhanced by the surface winds. The second thing were the two post-global dust storm years, Mars year 29 and 35. They have different areas than the rest of the data set. So Mars year 35 is slightly larger, and Mars year 29, it is slightly smaller, which was really interesting how the two post-global dust storm years have different trends among themselves too. So what we believe is happening is the timing of the global dust storm plays a really important role to how the seasonal cap reacts. Meaning that Mars year 34's global dust storm, which is this blue line over here, happens much earlier on, and that results in a larger cap for Mars year 35. whereas Mars year 28's global dust storm, which is this green line, happens much later on, and that results in a much smaller cap. We're not too sure like what exactly is happening. There's two main ideas that are kind of coming forth. First one is the early global dust storm results in a cooler surface, and the cooler surface enhances the formation rate, resulting in a slightly larger cap. And the later global dust storms deposits more dust over the seasonal cap, which kind of darkens the cap, and then that results in that results in a faster sublimation, and then resulting in a smaller cap when Marcy observations start. But there are a couple other ideas that could and just might work, but we still have to figure out exactly what is happening. So in the future, firstly, I want to add a dynamic HSV color detector. So right now, the code uses a static HSV bound, which seems to work, but there are certain images where there's a large enough dust storm that covers a significant portion of the cap, where it kind of changes the HSV value way outside the bounds. So by having a dynamic HSV bound detector kind of thing, we can accommodate for the changing and like even small dust storms and things like that. So I have written the core part of the code out, but there's so many parameters that still need to tweak to kind of make it like really robust. Second thing is repeat the same analysis I did for the northern seasonal cap, but for the southern seasonal cap, which you see on this right over here, this is another Marcy observation of the southern seasonal cap. And this is me just like running it once and just kind of seeing how it works with default parameters. And so the reason why the southern seasonal cap is much more interesting to me is that the southern polar region has many more anomalies. Like there's this thing called the cryptic terrain, which is a very dark region that like appears and we're not too sure why it's happening. There's like Swiss cheese patterns that are on the seasonal cap. We're not too sure why that's happening. So maybe the way that the seasonal cap moves might give us some insight to what's happening in the southern polar region. And yeah, thank you. Okay, any questions?
Nice work, Ruby. So I think like we did before, if someone wants to speak up and ask a question, feel free.
I would have a question. You mentioned that like the evaporation and condensation of the ice caps can cause pressure variations of like up to 30%, which I mean, that's really cool, honestly. And one method to like kind of track the ice caps is like by measuring, I think you mentioned where the temperature gets to 150, which is the sublimation temperature of CO2. Is this temperature, is this 150, does that depend on the pressure? And because I know for water, like the sublimation temperature might be pressure dependent.
I'm not too sure because like, of course it would matter, but I mean, that work was looking at the northern cap where the pressure where the pressure difference wasn't as large. It's like at most like probably like 10%. But it would affect it. But I'm not too sure exactly how the people that were looking at the spectral observation, how they accounted for that. I think as far as I remember, they were just looking at the 150-degree line. I don't think they were accommodating for the pressure changes and how that would cause the sublimation temperature to change.
Okay, thanks.
I think there was a question in something in the chat. Oh.
I've got lots of questions for Pruvi, but I'll save those for our group meetings. So Eve or Ahmad, do you guys, can we wrap it up? Or we have more time for questions.
Yeah, if
we have lots of time for questions.
Yeah.
So,
yeah.
Pruvi, can you talk about the quantity of images you're able to process and how quickly versus the manual method? Because it looked like you had 10 times more points than they did.
Yeah, for sure. So I'm not too sure exactly the exact time that they took to process their data, but when I was doing this like a couple of days ago, it took me about 1.5 minutes per like image. So it counted to, when I was doing it, counted to like 17 hours for 7 years, which is like a long time, versus my code does 7 years and 2.5 minutes. Yeah, it's just really quick, and like it's really easy to, let's say you want to account for the water clouds. It's pretty easy just to change a number up and you're kind of good in like 2.5 minutes compared to like redoing the entire work.
Yeah, this automation's been a really big boon.
Yeah.
And I like the validation that you had. So those groups, it's so time intensive that they only did a couple of years and then they stopped. They haven't done it again.
Yeah, they're only doing like 3 years. And with this automation method, essentially you just kind of press go and it'll just do all of your data sets instantly. Yeah, greatly saving a lot of time.
Great. Any final questions for Pruthvi? If not, let's thank him again. And let's thank both of our speakers and for all the trainees and everyone who gave their presentations throughout the academic year. So that's a wrap for this year. We'll take a bit of a break and pick it up again in the fall. So otherwise, have a great rest of the day and enjoy your summer. Bye, everyone.
See you, everyone.
everyone.